Okay, so just one little final note on this one. Did y'all get the same answer I did, 5 minus root 5? Okay, that'd be a good multiple choice or free response answer. Now, real quickly here, if that had not been x squared under the radical, let's kind of get rid of it. If that had just been an x under the radical, of course, then when you plug in, you would just end up with -1 like that. Would this be an okay place to stop on a free response question? No. Why not? Right. You have a negative under the radical now, and that is an unreal number. So this year, we're not working with imaginaries or complex numbers at all. It's the real number system, so that would actually be wrong. You would have to actually say non-existent or does not exist or, of course, DNE. So be careful. Don't get too comfortable with leaving things unsimplified. You should always, like when you're practicing, say, okay, here's where I would probably stop if it were a free response, and then you keep going so you can prepare for both types of questions. Got it? Okay, good. So then we're almost done with this section. It's not a very large section. There's one important theorem left to go. And we're going to have several theorems all year long. So theorems that have names are important, but theorems like Theorem 1.3 isn't as important a name as something like the Squeeze Theorem, okay? So when they have special names, they're even more important. So being a lunchtime class, 4th period, you could replace the word squeeze with sandwich, okay? Because this is sometimes called, especially around lunchtime, the Sandwich Theorem instead of the Squeeze Theorem, right? And they both imply what besides lunch? Maybe like squeezed lemonade, freshly squeezed, and a sandwich, maybe that's lunch. What do they both imply? Two things with something in between them, right? Yeah, very good. And that's exactly what the theorem kind of indicates. So here's what it says in the beginning. If, every theorem has two parts, an if and a then. The if part is the hypothesis, the then part is the conclusion. And of course, y'all learned in geometry the law of logical syllogism. If the if part is true in a theorem, then the then part is true. That's a great theorem. Okay, so this one says if you have three functions, g, f, and h, and if f is, for lack of a better term, squeezed between the function g and h, okay, the way you read that compound inequality is f is greater than or equal to g and less than or equal to h. That's how you read a compound inequality. Start in the middle. The alligator is eating the f on the left, so f is greater than or equal to g. And, not or, and f is less than or equal to h. So what that means for the most part is you have like a function like this, which can look like that, g of x. And then you've got this other function, h of x, which could look something like this. Actually, let me redraw that, something like this. That could be h of x. And then you've got f of x, which is going to fall between the two. Now, the equal sign means that it could actually equal it. So if you wanted to, you could draw something like this that falls between them, and it could like bounce off one and bounce off the other. So it can actually equal them. But if it doesn't equal them, it falls strictly between them, okay? So that's kind of where the squeeze or sandwich comes from. F of x is sandwiched or squeezed between h of x on the top and g of x on the bottom. Now, there's another part to this. For all x, except possibly at one specific value of x, except possibly at x equals c. That could be this one here. Okay, why is that possibly there? Well, you could have the h function, let's say the h function is undefined there. Let's say that the g function is defined there, but it's up here. And let's say that the blue function is actually continuous there. So it doesn't really matter what's happening at c, in other words, what the function values are. But everywhere to the left and everywhere to the right, f of x is bounded by h on top and g on the bottom. Okay? Well, then here's the and if the limit as x goes to that value of x called c of the bottom function g and the upper function h are both the same and they equal L, okay? So if you notice the way I drew those, I drew the pink lines and the blue lines on the bottom. I drew them going to the same altitude, the same y value at c. Who cares what the function value is doing? They have the same limit, right? Y'all see that? Then, and here's the upshot of it, then if all that's true, then there's no other option than for the limit as x goes to the same value for the function that's sandwiched between them at that same x value, it's going to get sandwiched or squeezed through the same thing, limit-wise. The roads are going to be squeezed through that same y value, okay? So basically, if h and g get squeezed through the point, not point, but through the limit value of c comma l, then any function that's contained between them have to get squeezed through that same limit value c comma l, right? So it's like when the bell rings here, most people head for that stairway, right? They come out of this room, the room next door, the room across, but you all get squeezed through that little stairwell. And then some people get smart and go that way and go down their stairs. And then some people go down that way and then come back after the stair clears, right? So you kind of avoid the squeeze theorem there. All right, so why is this useful? Well, it's useful if you're actually trying to find the value of the limit of a function like f of x at some value where you don't really know anything about it. If you are given, or in the real world really, if you can find a function that contains it above and below, ideally if you can then compute those limits of the h function and the g function at c, and they have the same, then you would have to then conclude, logically, then that's the limit of the function you're interested in, okay? So anytime you have a theorem like this, the use of the theorem is not going to be difficult. But what is going to be something that you have to learn is the formulating of your argument using the theorem so that you can get full credit, okay? So let me show you what I mean. You're not going to have to come up with the functions yourself. That's an entirely different thing, okay? But it's going to have a telltale ring to it. You're going to notice a question that involves the Squeeze theorem. It looks like this. If negative 3x is less than or equal to some function g of x, which is less than or equal to that quadratic. If it doesn't say where, you could assume it's for all x, okay? Find the limit as x goes to -1 of g of x. Well, how am I supposed to find the limit as x goes to -1 of g of x if I don't have a graph, I don't have an equation, and I'm not given information like I was up here about it, right? Well, the only thing I know is that g of x is contained between two functions, negative 3x on the bottom and x squared plus x plus 3 on the top. So let's see if I'm interested in what g is doing at -1. Let's see what the two functions that are bounding it or containing it are doing at -1, okay? So here's kind of what you would want to do. First things first, compute the limits of the upper and lower bound function at your desired value of x. So with the right notation, that's the limit as x goes to -1. And you can go ahead and just write negative 3x here because it doesn't have a name. And how would we compute that limit? Just by plugging it in, right? That's a polynomial. So is the top piece. They're both continuous everywhere. And so we know that they're also going to be the same as the limit value as the function value. So by direct substitution, you get positive 3. All right. So then you do the same thing for the other piece. The limit as x goes to -1 of the top piece. X squared plus x plus 3. If you have more than one term, you should probably write it in parentheses so that we know that we're evaluating the whole thing. So we can use that property of limits where we do each term separately, but not really here. We know it's another parabola, continuous everywhere. So by direct substitution, we get 1 minus 1 plus 3, which of course is 3. Now, those should be the same number. If those are not the same number, then the Squeeze theorem doesn't apply, and we just say something like, we don't know what the answer is, Squeeze theorem does not apply. But because they're both 3, we could then say, then okay, now we can go with our argument. So here's what you'd say. So since negative 3x is less than or equal to g of x, which is less than or equal to x squared plus x plus 3, okay, that was a given piece of information to you, but you have to cite that as one of the reasons in your argument, okay? Because if that were not true, the Squeeze theorem wouldn't apply, even if we got 3's up above. So because we got 3's above, and since that, we would then say the limit as x goes to -1 of our unknown function has to equal what? 3, okay? So the 3 components of the Squeeze theorem are, number 1, the computation of the limits at the lower bound and the upper bound. When they're the same, not necessarily if at this level, but when they're in the same, then you cite that the inequality is true, and therefore the answer that you're looking for has to also be 3. Okay, let's say that one comes out to be 3 and one comes out to be 2, right? That's not enough to say anything because you can have functions that look like this if they're not the same. There's x equals c. This one could be 3, and this one could be 2. And if you have a function that's still contained between them everywhere, what do we know? It could look something like this. How much space does it have to actually get quote-unquote squeezed through? How far is it between 2 and 3? It's 1 unit, which is an infinite distance, right? And between any two integers on the number line is infinitely many units, okay? So all we could say is that we know that the limit is going to be something between 2 and 3. Maybe 2, maybe 3, maybe 2.5. We don't know. But we can't pin it down to a single value because we're not really squeezing it, okay? By any standard, 1 unit might be relatively small, but it might as well be infinitely large, right? It's kind of interesting. If you think of the real numbers, here's 0 and here's 1, right? There's 2, 3, it goes on forever, -1, -2. There are different sizes of infinity, so it's kind of interesting that there are just as many numbers between 0 and 1 on the real number line as there are on the entire number line. That's kind of a weird paradox, right? It's the same size of infinity. Because you would say, no way, the entire number line is like infinitely bigger than the space between 0 and 1. But they're actually the same size of infinity. There's just as many spots between 0 and 1 as there are on the entire number line. Same size of infinity. Wow. Okay. Cool stuff. All right, so that's the squeeze theorem. So how do you know just by reading this then that it's going to be a squeeze theorem? What kind of triggers it? Yeah, we have two functions, and you've got this unknown function written between them, right? So in the compound inequality, these are going to be less thans. These will be less thans or less than or equal to. Oops, let me spell that right. These will be less than or equal to. Because this is the AND case, right? Let's review that real quickly here. If you say like 2 is less than or equal to x is less than or equal to 5, that's one way to read it. 2 is less than or equal to x, less than or equal to 5. But that's not the most meaningful way. This is the connected interval. It's the AND case. So you would say x is greater than or equal to 2 and at the exact same time less than or equal to 5 on a number line that looks like this. Here's 2, here's 5. They're both solid dots, and you're connecting the interval between them, right? So that's the AND case. It's both greater than 2 and less than 5 at the same time. That's what we reserve the compound inequality for. When you write it in one line with the x in the middle, we call that a compound inequality. We reserve the compound inequality exclusively for the less than. Okay, whereas if it were like this, x is less than 2 or x is greater than 5, this is a disjoint interval. I think we talked about this in pre-calc for a little bit. So that would look something like this. Here's 2. This one would be open, and we shade to the left. It would be 5. Let's put greater than or equal to. That would be closed, but then we shade to the right. It is impossible to be both less than 2 and greater than 5 at the same time. It is one of them or it's the other one. And because it's two disjoint, non-overlapping intervals, we always write it as two separate disjoint inequalities. We don't combine them. And in little school, you might have been able to get by with doing it this way. 5 is less than or equal to x is less than or equal to 2. Does that say the same thing? Kind of, right? The alligators are all eating the correct thing, yeah? When it's next to the 5, the alligator's eating the x. And when compared with the 2, the alligator's eating the 2, which is what we want. But this is like in English, you have rules, and then you have like slang, right, which you don't really use in proper. This is mathematical slang, okay? It doesn't really make sense to any person who really values math at all, okay? So when you'd use the less thans, you want to write them in increasing order. You got to have the small over here and the big over here, not flipped around, okay? So you got the disjoint case, which is two separate statements, and then you got the compound inequality, small less than or equal to x less than or equal to big. Okay, and that's the AND case. So that's the giveaway here. You have g of x, it's sandwiched between two functions, and you're looking for the limit of the unknown function. Okay, Squeeze theorem. All right, that's it. That's all I got. Any questions on this section? It's pretty easy. So rather than start the next section, because I think we're doing pretty well time-wise, I'll just give you the rest of the class to look at anything from 1.2 that you want to work on it. The key is posted, of course, and if you have questions, ask your math buddy. You can ask me. Tomorrow, we'll jump into 1.3. That's end behavior. If we can cover that in one day, I'd be surprised. That might take like a day and a half. That's end behavior limits, okay? And then we get to 1.4, which is kind of the fun section. That's all the algebra. That's where we're going to start evaluating limits by a bunch of algebraic methods.